Folks, good day. My name is Howard Preston. I'm a senior traffic safety engineer. I've been working on highway safety here in Minnesota for right around 50 years, and I've worked on the state system and local systems, helping public works agencies identify projects that they can deliver that will reduce the number of severe crashes out on the system. This is the second video of a three-part series on the Big Book of Ideas. Previous video, I discussed history and how to use the Big Book of Ideas. In this video, I will share with you the high priority safety strategies that have been identified for rural roads. That's segments, curves, and intersections. So let's get started with the rural strategies. The reason we're talking about rumble strips is that the number one severe crash on rural local roads and state highways is a single vehicle running off the road. And if you check back in with the NCHRP 500 series, the volume on road departure indicates that the number one safety strategies to address these road departure crashes is to improve your road edge. The notion being that if you improve the road edge, it prevents vehicles from getting off the road, and then what's beyond the road edge becomes immaterial. So the key strategy for rural road edges is a rumble strip. The traditional rumble strip has a vertical cut, and one of those concerns with rural areas in deploying rumble strips is that these vertical cuts generate traffic noise as vehicles run over them, and there's complaints from adjacent landowners. This has caused agencies to rethink this issue of deploying rumbles. And I'll just give you one example that one of the early implementers of a edgeline rumble strip was North Central Minnesota. Their county engineer was able to get a highway safety improvement program grant to do rural rumbles, and he selected a road as his number one priority. It had higher volumes, high speed, a high fraction of road departure crashes. But when you're first doing an implementation, you do not have the benefit of being able to look at what's come before, what other agencies have run into, either good or bad. He had not been able to anticipate that there would be complaints about traffic noise. He deployed the rumble strips, and it just happened that this segment of the adjacent land use was very expensive lake homes occupied by people who did not appreciate the traffic noise. And unfortunately, the complaints that these people made caused the county board to make the county engineer pave over the rumbles he had just paid to have cut in. And so that was a first sign that there would be some challenges associated with rural rumbles and that there needed to be thinking beyond the road edge about what the adjacent land use was. A new strategy since then has come up that addresses this issue of traffic noise. It's called a sinusoidal rumble or a mumble strip. You can see the photo of one in the lower left-hand corner of the slide. What's different is that there's no vertical edges, that this is a continuous cut that's a sine wave, but all of the rumble is below the surface of the road. Research has shown that the sinusoidal rumble has similar crash reduction capabilities similar to the vertical cut rumble, but has virtually eliminated complaints of traffic noise. I've checked with MnDOT traffic engineers around the state, asked if they've deployed the sinusoidal rumble, and where they have, if they've had any noise complaints. And anecdotally, I've been told there have been zero noise complaints associated with the sinusoidal rumble. A second advantage of the sinusoidal rumble, and again, you can see this in the lower right-hand corner of the page, is that if an agency puts their edge line or center line over the rumble, it's protected from the one thing that causes more damage to paint markings on roads, which is snowplows, because the entire cut of the sinusoidal rumble is below the surface of the road. The snowplows can't get down there. And what causes these lines, center or edge lines, to be reflective at night is actually glass beads that are embedded in the paint that cause this retroreflectivity, and snowplows scrape the beads off. But when an edge line or center line is installed in the rumble, the snowplows can't get down there and cut the beads off. And so the sinusoidal rumble has this added benefit of during night, and especially during wet pavement conditions at night, the edge line is the visibility is greatly enhanced. In addition to that, counties that have done this have shared that because the snowplows can't cause damage to the pavement markings, that instead of lasting a year or two before they have to be replaced, the counties are actually getting 5 to 7 years of service life out of the edge lines, and that's an additional benefit to reduce maintenance costs. The results of crash reduction for edgeline rumbles, again, you could see something on the range of 25 to 32 or 33%, and that the sinusoidal rumbles are very similar with the crash reductions. So the notion being, if you're in a place where there are no homes, it might be a hair cheaper to cut the vertical rumbles, and if there's nobody there to hear, then that's not a problem. But in any of the areas where there is adjacent residential land use, and especially where there are high traffic volumes, the sinusoidal rumbles look like they'd be a better investment, just because you'd eliminate any complaints of traffic noise. An alternative strategy to the edgeline rumbles is something called an enhanced edgeline, and that's either taking the edgeline from a traditional 4 inches to something either 6 or 8 inches, or in addition to that, there is a strategy that's called embedding the pavement markings. And so a trough about 1/2 inch deep, 6 inches wide, is cut in the edge of the pavement, and the pavement marking is put down at the bottom of that trough. And again, the idea being that putting the pavement marking down at the end of the bottom of this trough, the snowplows can't get to it. And there's a product then called a wet reflective pavement marking that uses a larger glass bead that is far more durable and reflective than under low light nighttime and wet weather conditions. And by putting the wet reflective pavement marking down at the bottom of this trough, again, the edge lines, center lines show up better at night and in wet pavement conditions, and the pavement marking material lasts again from something on the order of 5 to 7 years, which is probably 2 to 3 times what agencies would get out of a normal pavement marking put on the surface of the road. There is now additional reasons to think about this notion of trying to protect your pavement markings. Federal Highway just recently came out with a requirement that all pavement markings maintain minimum levels of retroreflectivity. This was not a requirement before, and it's similar to what Federal Highway did with the sheeting material that's on highway signs. 12 years ago, Federal Highway made it a requirement that agencies that put signs up maintain minimum levels of retroreflectivity. And that caused a great deal of consternation from the counties, in particular in cities, because their sign maintenance before that was way more ad hoc. They did it when they thought about it, and they didn't have to think about maintaining minimum levels of retroreflectivity. Now they do. This new requirement from Federal Highway says edgeline, centerline markings are now also going to have to maintain minimum levels of reflectivity, which will require counties and cities that put the pavement markings down to be more proactive about refreshing those markings. And yes, the research says there's an exception for lower volume roads, but with this requirement out there, I think it's going to become far more important for agencies to be aware of this and to be proactive on maintaining their edge and center lines. And again, one way of doing this is to embed them or put them in the sinusoidal rumbles, because then the snow plows can't get down and scrape the beads away. And the research says that the pavement markings will last probably 2 to 3 times as long as without taking that kind of precaution. All right, clear zone maintenance and enhancements. Again, we're talking about doing things that are mitigations for road departure crashes. So the first strategy, again, that was identified in the NCHRP 500 series documents, deal with your road edges. If you've done that and you're still having road departure crashes, the next thing to consider is providing a clear area adjacent to the edge of the road that doesn't have objects for errant vehicles to run into. And so the idea being the clear zone starts at the edge of the travel lane, includes the shoulder. It includes some kind of slope down into the ditch and some part of the ditch that again is suggested to be clear of any kind of fixed objects. Things that we put out there that people run into, sign supports, mailbox supports, have all been made crash worthy, meaning that the supports for the signs and mailboxes have been crash tested and then have been found designed such that they are unlikely to cause any injury if an errant vehicle hits them. So the number one thing that vehicles hit when they run off the road, according to crash data here in Minnesota, trees. More than a third of the road departure crashes involve a vehicle hitting a tree. And it's hard to imagine, but there are advocates for trees who would much rather have somebody run into a tree than cut that tree down. The idea again being, though, that trees are fixed objects, regularly are the object that vehicles hit when they run off the road, and a focus on trying to reduce the number of trees that are out there is part of this clear zone maintenance and would be available for highway safety fund investments. The first mention of clear zones in design guides, and there's an association, AASHTO, the American Association of State Highway and Transportation Officials. They are basically the professional organizations that represents the 50 state DOTs. AASHTO publishes design guides. The first mention of a clear zone was in the 1967 roadside design guide, which engineers called the Yellow Book because it had a yellow cover. So the first mention of clear zones was in 1967. AASHTO updated their roadside design guide in 1974 and came up with the notion of something called a forgiving roadside. And I find it quite amazing. We've been designing roads for at least 50 years by then, and nobody had really thought much about what was off the edge of the road. And it took AASHTO and then thinking about what are vehicles running into to come up with the idea that we really ought not to be hurting people or killing people with things that are along that road edge, because most of that kind of those obstacles can either be made breakaway or be relocated or be removed, and you remove the factor that contributes to so many injuries and fatalities associated with road departure crashes. The 74 AASHTO guide for the first time mentioned something called a clear zone, and then talked about a suggested width of clear zone would be 30 feet. And so that's again, from the road edge, shoulder, the slopes, some amount of the ditch, 30 feet clear. And the AASHTO, the yellow book, mentioned that this was based on observations on high-speed roadways. A clear zone of 30 feet from the edge of the traveled way permits about 80% of the vehicles leaving the road to recover. It also mentioned that this is based on observations of vehicle encroachments on roads with almost level roadsides, which really is not a very good description of most rural roads. We do not have roadsides that have that kind of grass shoulder extending out from the edge. And in fact, these observations were made at the General Motors Proving Ground, where there were no curves and the roads were basically tangent, and this infield area off the road allowed these vehicles to recover. The next AASHTO update was in 1977. The book still had a yellow cover, but a new title, Guide to Selecting, Locating, and Designing Traffic Barriers. And this update acknowledged that the recommended clear zone was not a constant 30-foot value, but variable, a function of roadway speed, slope, and an adjustment factor for locations along the outside of horizontal curves. Roads with higher speed, steeper slopes, and locations along the outside of the curves were considered to be the highest priority for providing wider clear zones. I was working with the Minnesota Highway Department when the 1974 Yellow Book came out with the recommended 30-foot clear zone. I sent staff out with a cloth tape measure and a can of yellow spray paint with the assignment to mark trees within the 30 feet of the road, with the idea that I would ask maintenance to go out and cut the trees. After about a week of marking the candidates for removal, I found out that maintenance sent out a crew with a can of green spray paint to cover up the yellow marks. They did not want to cut these trees. They were concerned about complaints by adjacent landowners, especially along Trunk Highway 96 in North Oaks. These trees were not removed until the road was widened about 20 years later. Around the same time, I was working on a project to improve the intersection of Trunk Highway 55 and Dakota County Highway 26, Lone Oak Road in Egan. The project would add left turn lanes and a traffic signal. The preferred design for the left turn lane would be to line them up, to have them head up on one another, so that the left turns could be accommodated more easily. The vehicles would be induced to turn in front of one another. But to provide this design would have required carving deep into this wide median, and that would have required removing an old oak tree that was in the median. When word got out about this possibility, the second grade class at the adjacent Trinity Lone Oak Lutheran School made the evening news one night when they came out and formed a human ring around the tree in an attempt to save it. It worked, and that staff told me to go with a design that did not take the tree. That is how the project was built, but about 5 years later, the tree died and was cut down. I did not attend the ceremony, but a friend from MnDOT gave me a small branch as a souvenir, and I have it in my basement workshop. One other roadside obstacle that is easy to overlook and is not as well known include field and driveway entrances. If these entrances have been in place for a while, they likely have slopes coming up out of the ditch steeper than 6-to-1. And this means that most vehicles that encounter them, the front bumper will dig into the slope before the wheels start climbing the slope. And that usually results in the vehicle flipping or rolling, and that can be a very bad day for the folks involved. Previous research on both MnDOT trunk highways and on the county system both show that rural roads with access densities greater than 8 per mile have higher crash frequencies than comparative roads with fewer accesses. I found that in rural areas, very few properties cross a half section line. That results in an average of 2 farm entrances on each side of the road in a mile for a total of 4 accesses. You throw in a couple of county or highway road intersections for another 4 accesses, and that gets you to 8 accesses per mile, which gets you the risk factor territory. You add in a few field entrances, and that road segment is then over the threshold. The graph you see on your left is for MnDOT trunk highways, and again, it shows at an average of 8 accesses per mile, crash rates increase substantially. And on your right is a graph from Minnesota's county highway system, where again, the red line is access density, the blue bars are crash percentages, and at 8 accesses per mile and over, you can see that the crash frequencies greatly exceed the crash densities are going up and up and up. And so the notion being that one candidate then for getting the county system back down under 8 accesses per mile is removing accesses. And I've been told by one of the county engineers in southern Minnesota, they went out and had a conversation with farmers along their county roads, found out that many of the field entrances that were being used are no longer functional because of the size of the farm equipment has gotten much larger. And what this county engineer did was made a deal with the farmers, give up 2 field accesses that are not functional because they're not designed well. And the county would provide 1 field entrance that was wide enough to accommodate all the new farm equipment, plus have slopes that were back to 6-to-1, so that if somebody did get into the ditch and encountered this field entrance, that they wouldn't have their vehicle go out of control because of the shallower slope would allow the vehicle to ride up and over that field entrance. All right, the next strategy we're talking about is chevrons, and the reason we're talking about chevrons, it's a curve strategy. And when we looked at the county safety plans again and looked at something on the order of 19,000 horizontal curves across the county system, a couple of things stood out. One, 50% of the road departure crashes occurred in curves, and curves make up around 10% of the county system by miles. And so you can see the curves are overrepresented in road departure crashes. The other thing that stood out is out of the 19,000 curves, 95% of them had not had a prior crash. So the notion is you can't use just the presence of a crash on a rural curve to predict the likelihood or probability of the next crash. And so we had to come up with a new analytical process that would allow us to predict out of all of these 19,000 curves, which ones were the highest priority, and that priority could not be made just based on the presence of a prior crash. So the 2 key questions again that we had to answer, which curves were overrepresented and were in fact then a good candidate for implementation of the safety improvements, and then what would be a good strategy based on cost effectiveness. So the answer to that first question involves identifying the characteristics of the curves where the severe crashes were occurring, and then conducting a comprehensive assessment of every curve in each county. And so, yes, we in fact did look at 19,000 horizontal curves and did a comprehensive safety assessment. And then the second consideration, what do you do to reduce these crashes? A traditional approach would be to reconstruct the curve with new and better design features. However, curves here in Minnesota are typically between a quarter mile and a half mile in length. Typical county road reconstruction is $1 million a mile. That means a typical curve reconstruction would cost between $250,000 and $500,000. Many of them would also have the added cost of having to buy additional right-of-way. If only 10% of the curves were considered high priority candidates, the construction cost would approach something on the order of $50 million. And with only around $18 million a year of safety funds dedicated for local system, the math just doesn't work. A less expensive solution to improving safety at curves had to be identified. That involves the installation of chevron warning signs. The cost is typically in the range of a few $1,000s per curve, as opposed to several $100,000 for reconstruction. And the research has documented crash reductions associated with the installation of chevrons to be around 25%. Just might be interested to know the first chevrons in Minnesota were installed along the segment of Trunk Highway 10 between Trunk Highway 61 and the St. Croix River in southern Washington County. The segment of Trunk Highway 10 was selected because it had many curves, but it was also the route that 3M executives used to get guests from their research facility in Cottage Grove to their favorite restaurant in Prescott, Wisconsin. These chevrons were installed by 3M by permit as an experiment. Chevrons were not yet an approved sign in the Manual on Uniform Traffic Control Devices. The experiment was basically designed by 3M's marketing department to highlight the benefits of high-intensity sheeting material, which was a new product being marketed and sold by 3M. Most other signs at the time were just engineering grade sheeting material, which wasn't nearly as bright. It turned out this was a very good experiment. The signs, chevron signs, after thousands had been deployed, have proved to be highly effective at reducing road departure crashes in curves. Right now, the idea of prioritizing curves, the first thing we thought about was curve radius, and the graph you see on the left side of this slide is from research that was done at Texas Transportation Institute that related curve radius and crash rate. And a couple of key points. It shows on the right side of the graph that at radii over about 2,000 feet, there is no additional risk compared to tangent sections of roadway. And then certainly by 1,500 feet or 1,000 feet of radius, the crash rate rises steeply. The graph on the right is from Minnesota's County Road Safety Plans, and the bar charts are crashes, the vertical lines. The red line is the frequency of curves in a range of radii, and what this graph shows is that at radii starting at 500 feet, the crash density is overrepresented compared to the total number of curves. So for the county road safety plans, the very first clue that we looked at was curve radius, and we measured curve radius using Google Earth. And somebody asked me once if I thought what our level of accuracy was. I'm confident it's certainly something near what plus or minus 100 feet. But it allowed us for the first time to measure the radius of every one of those 19,000 curves across all 87 counties. We needed something in addition to curve radius to help us understand the risk at horizontal curves. Another thing that showed up, a characteristic of curves, was curves that had an intersection in them were more at risk than curves that did not. And so the illustration on the left shows what's fairly typical in rural areas, the county or state highway with a horizontal curve, and then either county roads or township roads that tend to be built on a grid. intersecting with that state highway. So intersections in the curves were an additional risk factor. And then on the right, one of the things that we also observed while we were out doing road safety assessments of horizontal curves in the counties, something occurs that we called a visual trap. On the photo at the top of the slide, you can pick up, there's a utility line that's been traveling along the straight portion of the county road. You see the utility line extending on a straight line into the distance. You could see there's an edge to a woods that's in the distance that gives the appearance that the road goes straight, but that's a gravel township road, and we call this a visual trap. The paved road actually curves to the left, and the presence of visual traps also increased the risk at horizontal curves. So we ended up with a comprehensive list of 5 risk factors to identify curves. We included the presence of a prior crash, the range of curve radii between 500 and 1,200 feet, the presence of a visual trap, the presence of an intersection, and then daily traffic volumes in the range of between 200 and 1,500 vehicles per day. A demonstration of the effectiveness of this concept of applying the risk factors. The average density of severe crashes across 19,000 curves in the county system was 0.005 severe crashes per curve per year. But in curves with all 5 risk factors, the crash density was 0.02, 40 times higher. Very effective way then of identifying a much smaller subset of the 19,000 curves that were identified as being the best candidates for safety investment. The next strategy we'll talk about is streetlights at rural intersections. And the rationale for this is that at rural two-way stop intersections, right angle crashes are the #1 crash type. 36% of all crashes and 65% of fatal and serious injury crashes. Traditional strategies included overhead flashers, transverse rumble strips, based on the notion that running the stop sign was the primary contributing factor. However, research found that overhead flashers didn't work. Plus, a study done by the University of Minnesota in their driving simulator found that about 1/3 of the drivers in an experiment assumed that the presence of an overhead flasher indicated an all-way stop. That's a very dangerous piece of information to put in the mind of drivers, because then drivers are assuming that other vehicles on the cross traffic approaches would also be stopping when that wasn't the case. Some studies have shown a reduction. Other studies have shown an increase. Conducting before-after studies at rural intersections is challenging because of extremely small sample sizes of crashes and difficulties in determining when before stopped and after started. What I consider to be the 2 most definitive, the effectiveness of transverse rumble strips is inconsistent. Some studies have shown a reduction and others an increase. Conducting before and after studies at rural intersections is challenging because of small sample sizes and difficulties in determining when before stopped and after started. What I consider to be the most definitive study was done by Iowa State University, and it overcame these 2 challenges. The rest of the story: a crash occurred at a rural intersection on the county system, and a county in Iowa was sued for negligence and lost based on the claim that the crash would have been prevented if only the county had installed transverse rumble strips. After the lawsuit, virtually every county in Iowa installed transverse rumbles at virtually every intersection on their system. This solved the problem of small sample size, because the number of intersections involved was around 2,500, and the before-after date for the installation of the rumble strips was known, the year after the first county had lost the lawsuit. The Iowa State research found that both the total number of crashes and the number of right angle crashes increased after the rumble strips were installed. Subsequent research done in 2001 by the University of Minnesota addressed the issue of primary contributing factor to right angle crashes. A total of 1,604 rural intersections were reviewed, where a total of 639 right angle crashes had occurred. The study found that 90% of the intersections had no run the stop crashes, and that only 25% of the angle crashes had run the stop as a contributing factor. Almost 60% of the right angle crashes involved a vehicle stopping and then pulling out. This research suggests that the primary factor contributing to the majority of right angle crashes was poor gap selection and not run the stop. The study also found that 20% of the ran the stop crashes occurred at night and at intersections without streetlights. This is twice the statewide average for all crashes and was an indication of the possibility of considering the installation of streetlights at rural intersections as a safety strategy. A follow-up study in Minnesota found that streetlights were rarely installed at rural intersections, and this was primarily due to MnDOT policies at the time that required a prior nighttime crash, which is rare, signal warrant volumes, meaning very high traffic volumes on both the minor and major legs, which is also rare, and that if a street light were installed, local agencies had to agree to pay for the power. This study also looked at national research that documented crash reduction in the 25 to 35% range, and that the benefit cost ratio associated with the installation of streetlights at rural intersections was 15-1. All of this suggesting that the installation of streetlights was a highly effective strategy for reducing the number of crashes at these rural intersections. A part of county road safety plans, approximately 200 rural intersections have been installed. It should be noted that the effectiveness of streetlights is not a function of the amount of light that reaches the road surface at the intersection. A luminaire on a davit arm on a utility pole in the corner of the intersection has proven to be as effective as the standard MnDOT design, which has the luminaire much closer to the intersection. Some counties have found that the installation cost can be as low as zero. Some rural electric utilities have installed the pole, davit arm, and luminaire at no cost, which means then the county only has to pick up the monthly power costs. Final story about the rural streetlights. A senior county engineer installed the streetlights in his county, the first ones as a result of recommendations in his safety plan. Sometime afterwards, he called me and shared that after the streetlights went in, his phone started ringing. And for the first time in his career, residents were asking for the same treatment at their nearby intersection. The public liked it. Another strategy to deal with severe crashes at rural intersections includes upgrading signs and pavement markings. Again, the rationale being that angle crashes are the number one severe crash at this type of two-way stop controlled intersection. Strategies that have been tried to address these crashes include oversized stop signs, reflective strips on signposts, and the addition of flashing LED lights to the stop signs. All of these features are intended to call more attention to the stop sign in an effort to reduce run the stop crashes, and the effectiveness has been mixed. For example, a study done by the University of Minnesota found that flashing LEDs on the stop sign did not reduce crashes, but did result in a small reduction in approach speeds. One additional strategy involves painting a stop bar, not at the traditional stop sign location. It is typically 30 to 40 feet from the through road, but instead at a location that is approximately 10 feet from the through roadway. This is based on intersection sight distance characteristics, an attempt to help drivers make a better choice relative to selecting a gap. As part of county-wide road safety assessments I've participated in, I've had the chance to stand on the minor road approaches to dozens of rural intersections. I would stand at the stop sign and check the sight triangles, which are illustrated in the intersection diagrams on the left of the slide. At the typical stop sign location, 30 to 40 feet back from the through road, my line of sight was regularly intercepted by things like trees or corn or tall grass, because at 30 to 40 feet back, you are standing behind where the ditch is, and it's an area that doesn't get cut by maintenance crews. Any driver that stopped here faced two challenges. First, they would not have a clear view of any oncoming traffic, and it would take several seconds to complete their turning or crossing maneuver compared to starting from a position closer to the through road. During these road safety assessments, I would walk up to the intersection from the stop sign, and invariably my line of sight would open up. It was ahead of the trees, ahead of corn, or of tall grass. Placing a stop bar at approximately 10 feet off the through road provided better sight lines, which allows for better gap selection. It was also a more advantageous position to start from because less of the typical 10-second gap used by most drivers was used to get from a starting position to the through road. More of the 10-second gap would then be available. The next rural intersection strategy that we're going to discuss is something called a J-turn or an R-cut intersection. R-cut stands for restricted center U-turn. The rationale is that the most common type of severe crash at full open expressway intersections is a right angle crash, and approximately 75% of these crashes occur on the far side of the intersection. It appears that drivers on the minor roads can clear the near lanes with very little problem, but for a variety of reasons that nobody has fully documented, the far side of the intersection is far more at risk. In the early 2000s, only two potential strategies were available to address these right angle crashes. Traffic signals, but even then we were beginning to understand that in the long term, traffic signals did not really improve safety at these kinds of intersections. And the second strategy was to build an interchange, but with a $25 million price tag, interchanges could not be widely deployed using the very limited highway safety funds that were available. In 2010, NCHRP, National Cooperative Highway Research Program, Report 650, Median Intersection Design for Rural High-Speed Divided Highways, was published and included a description of the development of an innovative intersection design, the J-turn. The case study described the design and crash history at the intersection of US 301 and Maryland 313. The intersection was a typical expressway design with two-way stop control on the minor road approaches. The intersection averaged about 8 crashes a year, of which 75% involved injuries, 70% were right angle crashes, and 80% of those occurred on the far side of the intersection. The Maryland DOT had intended to address the crash problem by constructing an interchange, but financial problems forced them to work to develop a less expensive at-grade solution. Given the crash characteristics, designers focused on preventing the minor road crossing maneuvers, which was the primary factor contributing to the right angle crashes. They came up with the idea of substituting a right turn followed by a downstream U-turn followed by a right turn for the prohibited crossing. The new acceleration and deceleration lanes, plus the new directional median openings, were constructed for approximately $650,000, about 3% of the cost of the previously planned interchange. Following the construction of the J-turn, total crashes were reduced by 90%, and injury and right angle crashes were reduced by 100%. Subsequent studies in Minnesota have found similar crash reductions. As was the case in Maryland, severe crashes at Minnesota's expressway intersections are primarily right angle, with the majority occurring on the far side. As a result, J-turns generate safety benefits by eliminating crossing conflicts, which are the primary contributing factor to the angle crashes, substituting merge-diverge conflicts for the crossing conflicts, taking advantage of the fact that right turn and left turn maneuvers have lower crash involvement rates. The graph on the right side of the slide shows that in Minnesota, right turn maneuvers contribute to about 1% of crashes. Left turn maneuvers contribute to about 5% of crashes at these rule through stop intersections. But angle crashes are over 40%. So this is again supporting the notion of why Maryland came up with this idea of restricting the median, substituting the right and left turns for the crossing maneuver, eliminating the crossing conflicts, and then substituting merging and diverging conflicts. One other advantage of this design is that it reduces the kinetic energy that's associated with any subsequent crashes by reducing crash angles from 90 degrees to something on the order of 20 to 30 degrees. The J-turn results here in Minnesota are really outstanding to show how this strategy can reduce crashes at these types of rural expressway intersections. Again, the table on the left shows fatal and serious injury crashes reduced by almost 70%, and that the bar chart on the right is a comparison of J-turn crash rates compared to crash rates at similar intersections with signal control and similar locations that had low volume interchanges. The bar chart shows that the J-turn is superior from the perspective of total crashes, from the perspective of injury crashes, and from angle crashes. And that's even compared with interchanges, which again are orders of magnitude more expensive. The first three J-turns in Minnesota, so a history lesson. First one was installed at Trunk Highway 169 in Belle Plaine. The second at Business 71 in Wilmer, and the third along Trunk Highway 53 in Cotton, Minnesota, which is about 100 miles north of Duluth. All had one thing in common. The public and elected officials thought the idea was idiotic and counterintuitive. How could three turns be safer than the simple crossing maneuver? And why don't you just put in a traffic signal? Belle Plaine was first. The county had two accesses. The city had two accesses across Trunk Highway 169, both county roads. A north access that had a traffic signal and a south access that was two-way stop controlled. At some point, MnDOT and Scott County agreed to replace the traffic signal at the north access because of the number of crashes. During the construction of the interchange, the signal was moved to the south access in order to accommodate detour and construction traffic. Prior to completion of the interchange, MnDOT and Scott County discussed what should happen at the south access when the interchange opened. They considered that the traffic signal should be removed because they had just invested $25 million at the north access to mitigate the crash problem associated with the traffic signal. The agencies also concluded that they shouldn't leave the median at the south access open due to concerns about the documented safety problems associated with the crossing maneuver. As a result, they proposed installing a J-turn. At a public information meeting, the public and local officials were not convinced by the results from Maryland and refused to provide the required municipal consent. At this point, Scott County determined that they had to do something, so they used their own maintenance forces to remove the median opening, thereby preventing the crossing maneuver. A year later, city officials approached Scott County and requested that the J-turn be reconsidered. It was then constructed, and a follow-up study a year after construction found that there had been no crashes at the intersection. Wilmer was second. The intersection of Business 71 and Candy-Ojai County Road 24 had a two-way stop control and a history of approximately 5 crashes per year, all of which were right angle. MnDOT attempted several low-cost mitigations, a larger stop sign, rumble strips on the approach to the intersection, and flashing LED lights, all in an effort to call greater attention to the stop condition. But none of these devices reduced crashes. A road safety assessment was then completed. The RSA included a more in-depth analysis of the crashes and determined that the crashes were not associated with vehicles not recognizing the stop sign, but instead were associated with vehicles attempting to cross the highway and making bad decisions about gap selection. The RSA evaluated a variety of alternative solutions, including traffic signal, but concluded that it was unlikely to result in a crash reduction, an interchange, which was too expensive, and finally a J-turn with support based on the recent success at Belle Plaine. MnDOT brought the J-turn to the City Council for municipal consent, which was denied. MnDOT returned to the city each of the following years, again trying to secure their consent, which was again denied. Finally, 3 years later, and after several additional crashes, the city provided their consent and the J-turn was constructed. A follow-up study conducted a year later determined that there had been no crashes. When informed of this, one of the city councilors that had been opposed to the J-turn admitted to a local newspaper that it appeared he had been wrong and had to eat crow. The J-turn at Cotton was third. Similar to Belle Plaine and Wilmer, the intersection of Trunk Highway 53 and St. Louis County Highway 52 had a history of crashes. A road safety assessment was completed and found that the intersection averaged 4 crashes a year, most involving injuries, and all were right angle. The RSA evaluated alternatives, including lowering the speed limit, which the State Patrol determined they did not have enough officers to enforce a lower limit, a traffic signal, and that staff concluding that that would unlikely reduce crashes, an interchange, and designers concluded that a typical interchange would wipe out businesses located in 3 quadrants of the intersection, and then a J-turn. As was the case in Belle Plaine and Wilmer, comments at the public meeting in Cotton were entirely negative, and local township officials were unconvinced that the safety benefits cited from Maryland, Belle Plaine, and Wilmer. Township officials informed MnDOT that they would not provide their consent. However, unlike Belle Plaine and Wilmer, it was determined that consent was not required from the township, and MnDOT and the county moved ahead and constructed the J-turn. A follow-up study found that in the 10 years following the construction, there was only one severe crash, and it involved a vehicle that was illegally crossing Trunk Highway 53 through the restricted median. MnDOT has now constructed 106 J-turns along the state's expressway system. A study recently completed by MnDOT safety engineers found J-turn construction resulted in 76% lower crash rate 50% reduction in fatal and injury crash rate. J-turns have a 57% lower crash rate than expressway intersections with traffic signals, 54% lower crash rate than low-volume expressway interchanges. J-turns have a 75% lower right-angle crash rate compared to signalized expressway intersections. All of these differences are statistically significant. The key takeaways: J-turns have demonstrated a great crash reduction, have a better safety performance than low-volume interchanges, and you could build 25 J-turns for the price of one interchange. Final point: if I could be commissioner of the MnDOT for a day, I'd institute a policy that said no full open expressway intersections, only right in, right out, J-turns, or interchanges. Another strategy that's associated with rural intersections is involving changing the skew angle, the angle at which the minor road approaches a major roadway. And again, the notion is the number 2 crash type across the entire county system is angle crashes at intersections. And it's been found that angles other than 90-degree of approach on the minor road are associated with higher crash densities, crash rates, and crash severities compared to 90-degree approaches. And so the idea, again, being reconstructing these skewed approaches can provide crash reductions in the neighborhood of around 30%. One additional lower cost strategy for rural intersections, again, the idea being safety concerns at rural intersections are the number 2 priority for rural counties, includes involving the construction of turn lanes on the major road. And the idea of providing these turn lanes has resulted in a crash reduction somewhere in the neighborhood of 15 to 20% of all crashes and all crash types. And the cost of providing the left turn lanes is somewhere in the range of $30,000 to $200,000. A final intersection strategy for rural intersections involves roundabouts. So again, the rationale, the number 1 severe crash type at rural intersections is a right angle crash. We know that the minor road crossing is a primary contributing factor and that traffic signals are not safety devices at these rural intersections. Roundabouts have an outstanding crash reduction that's in the range of 80 to 90% of fatal and serious injury crashes. The crash reduction is primarily due to 2 factors. First, kinetic energy of any crash is reduced because of the lower speeds through the roundabout, and impact angles are reduced from 90 degrees to something on the order of 20 to 30 degrees. Second, the roundabout eliminates the crossing conflicts that are the primary cause of right angle crashes and substitutes merge diverge conflicts that have a much lower crash involvement rate. Folks at the workshops have asked about the effect roundabouts have on pedestrian crashes. A study done by the university of 10 years ago couldn't find enough pedestrian crashes at roundabouts to support a statistically reliable conclusion, but did point out that features associated with roundabouts are also considered to be associated with improved pedestrian safety: lower operating speeds, one-way approaches, and median refuge islands. That study also noted that roundabouts had better yielding rates than comparable stop-controlled intersections. A recent study conducted by MnDOT did find enough crashes to yield statistically reliable results, included that roundabouts did improve pedestrian safety compared to traffic signal and stop-controlled intersections. One final point: if you are considering converting an intersection to a roundabout, roundabouts treat all of the approaching legs equally. ask yourself if from a functional classification and traffic volume perspective, should the legs be treated equally? To wrap up the discussion of roundabouts, MnDOT installed 3 roundabouts along Trunk Highway 316 in the city of Hastings in Dakota County. This construction resulted in a 70% reduction in injury crashes. This wraps up the discussion of rural strategies, and we'll take up another discussion then of urban strategies in the next video.